Okay, so this is the movie clip number 3 for week 10. So, as I told you, in this movie clip, we are going to study the concept of quasi-Fermi levels. So, as described here, excess electron concentration and excess hole concentration is non-zero. In other words, some other external force has been applied so that the total number of electron hole concentration has been modified away from the equilibrium electron hole concentration so that mass action law cannot be applicable, cannot be valid at all. However, this is the desire that of us. We would like to what? Preserve, still use the relations such as this NMP. You know the 60 millivolts law. Once you know the multiplication of for number 6, then we can very simply estimate the position of Fermi energy level in the Venn diagram. So electron concentration, hole concentration is the function of Fermi energy level. But this E sub F is only valid when the excess carrier concentration is zero. In other words, at thermal equilibrium, those two equations, number 1 and number 2, those two equations are available and valid only. However, we would like to preserve those two equations. How? Yes, in order to preserve those two equations, number 1 and 2, we can introduce two quasi-Fermi energy levels denoted as F sub n and F sub p. Then we can write down the same form of equation 1 and 2 for n and p, even though this electron and that hole concentrations are not obtained at thermal equilibrium. We can still use the same format of the equation if we can adopt quasi-Fermi energy level denoted as F sub n and F sub p. Then we can preserve those two equation formats. So by solving a single example problem, we can better understand what the Fermi energy levels, quasi-Fermi energy levels are. Let's consider a silicon sample with a doping concentration N sub D of 10 to the 17 per cubic centimeter, and the excess carrier concentrations are 10 to the 14 per cubic centimeter. What are the P and N? So P and N. First, this silicon sample is doped with donors. So this is an N-type silicon sample. And the question is P and N. Um, First, this is the N-type. So at thermal equilibrium, the electron concentration is identical to the N sub D, so 10 to the 7. And using the mass action law, we can have the minority carrier concentration at thermal equilibrium. Okay, so 10 to the 17, 10 to the 10 square. So the answer is 10 to the 3 per cubic centimeter. All right, but the question is P and N at non-thermal equilibrium state. So N is equal to what? Yes, delta N plus N naught, because what? Delta N is defined as N minus N naught, so we can get N is delta N plus N naught. So delta N is given 10 to the 14, and N naught is 10 to the 17, so that 10 to the 17, because 14, 17, you know, the difference is 1000, so we can ignore this number. So this 10 to the 17 is equal to N naught. So the majority carrier concentration of N-type silicon material has not been affected by this excess carrier concentration. What about the minority carrier concentration in N-type silicon material P? What happens to P sub N? Delta P N plus P N naught, right? So what is a delta Pn? Yeah, there we go. Or even though I haven't used the subscript, but we talked about the N-type silicon material. So that is 10 to the 14 plus Pn naught. What is it? Yeah, there we go. I didn't include the subscript to indicate the material type. But anyhow, that is a P and not, right? So that was 10 to the 3. So 14, 3. You can ignore this number. So that is 10 to the 14, which is much higher than Pn naught. Okay, so Pn is much higher than Pn naught. In other words, in n-type silicon material, the minority carrier concentration has significantly affected. Okay, all right. Now the second question is the NP product, N times P. So N times Pn, because we are talking, all the question is regarding the n-type silicon material. So Nn is here, and Pn is here. Then 17 plus 14, that is 31. Okay, that is much higher than Ni squared. That is 10 to the 20. 31, 20. So much higher. Okay. Then the third question is find out the quasi-Fermi energy level for electron and quasi-Fermi energy level for hole. So using the same equation format, n is equal to ni exponential ef minus ei over kT. But herein, I'm going to use a quasi-Fermi energy level. Okay, if I'm using E sub f, that means n naught. But if I'm using quasi-Fermi level, that is a non-equilibrium electron concentration. Then you can move all the other terms. Ni is here, n minus n divided by ni is equal to exponential fn minus ei over kT. And then, fn minus ei over kT is equal to take a logarithmic log. So ln, that is here, and then n over ni. And then kT move to the right hand side, so fn minus ei is equal to kT ln n over ni. There we go. So quasi-Fermi level fn is ei plus what? KT ln n over ni. Okay, so now we are ready to plug in the value. So what was the n value? 10 to the 17, and ni is 10 to the 10. So 17 divided by 10, so 17 minus 10, 7. So ei plus kT, and then 10, 7. So 7 comes out, and ei plus 7 times kT and 10. So kT and 10 is 60 millielectron volt. Okay, 0.06 electron volt times 7. So if I draw the energy band diagram, you see there is an intrinsic Fermi energy level, which is corresponding to the mid gap. Then 7 times 0.06. So about here, 0.426 electron volt. Okay. All right. Similarly, you can repeat the calculation for F of P, F sub P, and you're gonna end up with 4 times kT ln 10. Oh, I missed the EI. EI minus 4 times kT ln 10. So F sub P, the quasi-Fermi energy level for hole, is EI minus what? 4 times 0.06 electron volts. So 4 times 0.06, 0.24. So F sub P is 0.24 electron volt. Okay, so now since this n-type silicon material is not at thermal equilibrium, we're gonna have a two different quasi-Fermi energy level. At thermal equilibrium, we have a single Fermi energy level, but at non-equilibrium state, two different Fermi energy level named as quasi-Fermi energy level. It is not the exact Fermi energy level, but we can use, because we would like to preserve the prefer the equation format, and this guy, right? So we have introduced two different concepts: quasi-Fermi energy level for electrons and the quasi-Fermi energy level for holes. So F sub n and F sub p. Those are two Fermi quasi-Fermi. This is not real Fermi energy level. Quasi means not real, fake. Okay. So the quasi-Fermi energy level can be used to still preserve this very useful equation. So F sub n, F sub p would then f sub n and f sub p would become a good indicator how much electrons and holes are included in this n-type silicon material. So if once you take a look at the f sub n, this energy difference Fn minus Ei indicates the 0.42 electron volt, indicates how many electrons are included in this n-type silicon material at non-thermal equilibrium state. And this energy difference, Ei minus Fp, quasi-Fermi energy level for holes, Ei minus Ef, this energy difference gives us an idea how many holes are included in this n-type silicon material at non-thermal equilibrium state. Okay, so F and Fp still are very good, useful indicators to know how many electrons, how many holes are existing in the n-type silicon material. Okay, so that's all for the lecture note number 10. So please take a look at the summary by yourself. So we have learned the continuity equations, minor-to-carrier diffusion equations. Afterwards, we have understand minor-to-carrier diffusion lengths, the definition of it. And later on, we have introduced the quasi-Fermi energy level to indicate how many holes, how many electrons are available in a silicon material at non-thermal equilibrium. That's all. See you in the next movie clip. Bye bye.